Our last video showed the equal-shaped relationship between the symmetries of an equilateral triangle, D6, and the permutations of three objects, S3. We called these two groups isomorphic. In this video, we'll explore characteristics of the isomorphism that we can use in our study of group theory. Recall our homomorphism equation. Now, let's show our mapping phi from D6 to S3 as a bijection. Both 1-to-1 we call injective, and onto we call surjective. Phi is 1-to-1. Each element in the domain is mapped to a unique element in the range. No two elements from D6 end up as the same element in S3. A benefit here is that we get an inverse function, a map back to the original group. The reflection R goes to the transposition 1, 2, but we can also go back from the transposition to the reflection. For this to hold on the entire group, there must be as many or more elements in S3 for all of the elements in D6 to map over to. All 6 elements, E, A, AA, R, S, and T, have a unique place to go in S3. Second, phi is onto. Something is mapped to each and every element in the range S3. Remember our example Z12 to S2 mapped even elements to the identity and odd elements to the transposition? With only 2 elements in the range, the identity and the transposition, that map was onto. However, those two groups were only similar shaped, not equal shaped. To be onto, there must be at least as many or more elements in the domain, D6, to cover all of the elements in the range, S3. How can there be at least as many or more elements in S3 than in D6, and be at least as many or more elements in D6 than S3? This can only happen when both D6 and S3 have the same number of elements. For an isomorphism, the mapping is 1-to-1 and onto, called a bijection. 2 isomorphic groups have the same number of elements. Recall under our mapping phi, we get the same answer performing the operation in the domain and mapping the answer to the range, or if we map the element over to the range first and then perform the operation in the range. One thing we observe, if the identity is involved, performing the function in the domain gives us the same element. Alpha star identity leaves alpha. And if we map phi alpha over to the range, we see the only way the equation works in the range is if the identity maps to the identity. We can make the same identical argument for identity star beta. Our answer on the left is just beta, and we map phi of beta. The right side can only be true if the identity maps to the identity. Another characteristic of the isomorphism is it always maps the identity to the identity. The reflection about 150-degree axis in D6, the element S, has an order of 2. It is its own inverse. Our equation, alpha and beta, both being S follows S on the left, is the identity. We also know that S mapped to the transposition 1, 3 in S3. And if we perform 1, 3, we see the only way to return to the identity on the right is to perform 1, 3 again. Since this simple case of a transposition element is its own inverse, the inverse of S on the left actually maps to the inverse of S on the right. And we can check the inverse elements all map to the inverse elements. In D6, A and AA are inverses. We can perform the 120-degree rotation, element A, then the 240-degree rotation, element AA, and we see the identity. With A mapped to 1, 2, 3 and performing 1, 2, 3 on the right, we see the element that will take us back to the identity is 1, 3, 2. Again, the inverse element maps to the inverse. While not a mathematical proof, hopefully through intuition and through some basic inspection of the equation, you can see the inverse of an element in the domain always maps to the inverse element in the range. The final characteristic of isomorphisms we will show. Inverse maps to inverse. Isomorphic groups have the same number of elements, which makes sense if they're equal shaped. There must be a bijection, a map from the domain to the range that is both 1-to-1, each element is mapped to a unique element, and onto, all elements in the range get mapped. In that map, the identity element will always be mapped to the identity, and an element's inverse will always map to the inverse of that element in the image. In this video, we showed some characteristics of an isomorphism, a bijective map between two groups where the identity is mapped to the identity and inverses are mapped to inverses. In our next video, we will cover a different group representation and make a powerful statement about isomorphisms mapping to a group or subgroup of a group of permutations. We hope to see you in that video, and if you like these videos, please give them a thumbs up or a comment down below and help the channel grow by telling a friend or becoming a subscriber.